As we continue to review concepts from number theory, what we'll be discussing in these collections of videos is the greatest common divisor of two integers and the Euclidean algorithm, which is a process by which we can come about finding the greatest common divisor of two integers. So right here, I'd like to provide the formal definition for you of the greatest common divisor of two integers. And to help you keep track of the requirements, I've enumerated them to take this definition apart piece by piece. Now, luckily for us, the definition of this seems very natural. So to begin, we're going to assume that we have two non-zero integers, a and b. We want both of them to be larger than 0 because we're talking about divisors and division, and generally dividing by 0 is something we shy away from. We're going to denote the greatest common divisor of two integers like a Cartesian or ordered pair, parentheses around the a and the b. We should note that some textbooks, including Gallien's book, which is our official textbook, are a little bit less sloppy than I am with the way they denote the GCD of A and B, which is by putting the letters GCD in front of those parentheses. This is the way our textbook writes it, and this is the way that I write it. And I can try to be more consistent with one notation over the other if you have a preference as a class. But back to the definition of the greatest common divisor of two different integers, a and b. First of all, we want the greatest common divisor to be a divisor of a. Similarly, we'd like the greatest common divisor to be a divisor of b. And so 1 and 2 combined is giving us the common divisor portion of this definition. And part 3 of our definition is taking care of the greatest part. So once we have a common divisor of the integers a and b, we want the largest number that satisfies properties 1 and 2. And when those things are done, we'll have the greatest common divisor of these two integers. Along with this definition is another definition which will be incredibly important to us. If we have some numbers that happen to have a greatest common divisor being 1, notice that 1 will always satisfy 1 and 2. 1 divides everything. So certainly 1 will divide A and 1 will divide B. If we happen to be in a case where there's no bigger number than 1 that does 1 and 2, then there's a special relationship between the integers A and B going on, and the name that we'll use for that special relationship is that those two integers are coprime, or occasionally we'll say that they're relatively prime. We need to be a little bit cautious, particularly with this second definition of coprime. It automatically makes you think of the concept of primeness and prime numbers, but the relationship might not be as clear as you want it to be. For example, if we have one of the two numbers a and b being prime, that doesn't guarantee that a relationship with another integer is a coprime relationship. So for example, if I were computing the greatest common divisor of 7 and 28, that would be 7, because 7 divides 7, 7 divides 28, and clearly nothing larger than 7 will work to divide both of them. So the greatest common divisor of 7 and 28 would be 7. So one of these numbers being prime doesn't automatically guarantee that you have a coprime relationship. And it gets worse because on the other hand, you can have two numbers, neither of which is a prime number, but where the relationship between the two numbers is a coprime relationship. So for an example of that, let's think about 15 and 28. 15 is 3 times 5, 28 is 7 times 4. The only thing that divides both of them is the number 1. And so neither 15 nor 28 is a prime number, and yet these two numbers are coprime to one another. So just be cautious of that as you're thinking about greatest common divisors. Now I'd like to give another example of how we go about computing greatest common divisors. The way that I would start is a little bit ad hoc. How would we compute if I give you a different example, numbers like 216 and 396? Try to think about how would you find divisors of those numbers? And then how would you find the greatest common divisor? Take a minute, pause, think about it, brainstorm. When you're ready, unpause the video. Well, there might be lots of different ways. Whatever you might have been thinking of, it probably could have been done. But some things that I've heard frequently, as I've discussed greatest common divisors, is maybe we list out the divisors of all the numbers. Sit down, look at 216, list out the divisors. List out the divisors of 396, and then compare those lists. Another thing that might come to mind is divisibility tests. Although this is not standard, it may depend on your elementary school education. I learned a whole bunch of little quick rules for determining if a number is divisible by a particular prime. For example, I know that a number is divisible by 5 if it ends in a 5 or a 0. I know that a number is divisible by 3 if the sum of its digits is divisible by 3. There are a handful of little ad hoc rules you can learn for different numbers to determine what they're divisible by, and so you might be able to use divisibility tests to figure out common divisors of these integers. Another thing you might have done is use the prime power factorization of these two numbers, which we'll talk about further in another video, or you may use a factor tree to figure out all possible prime divisors of these numbers. That's another route that you could take, which I'll show you more of. And then there are definitely ways that I'm missing that could have been used to solve this problem. So if you'd like a little bit more information on any one of these methods, I'll briefly go over them and I can elaborate if need be. Listing out the divisors. This one is perhaps the most straightforward and caters the most to the definition we have. I could just blatantly list out the divisors of each number, look at these lists, and find the largest number that appears in both lists, which happens to be 36. I could use divisibility tests. There's a divisibility test for 4. If the last 2 digits of a number is divisible by 4, then the number itself is divisible by 4. So I could create a simpler problem by just looking at 16 and 96, which are the last 2 digits of these numbers. And I could say, sure, each of these numbers is divisible by 4. So certainly both numbers are divisible by 4. Similarly, if the sum of the digits of a number is divisible by 9, then each number is divisible by 9. That happens to be the case for each of these numbers. The sum of these digits is 9, and the sum of these digits is 18. Both of those are divisible by 9, so the whole number is divisible by 9. And that means that 36 divides 216. And when I do 216 divided by 36, or 396 divided by 36, I get 6 and 11. And those numbers are definitely coprime. So that would tell me that this is the largest divisor that divides both of them. Another thing you might have done as a child is used factor trees, which is where you look at a number like 216 and you pick some sort of obvious to you divisor, like 4, and you break 216 down as a product of 4 and 54. You then repeat this process for each of these numbers, picking a divisor that seems obvious to you, and you break it down until you find the leaves of your factor tree, and the leaves of your factor tree are prime numbers. So I could do this process again for 396, and then by combining the leaves in exponential notation, I am going to get what's called the prime power factorization of these two numbers. And then what I can do is go through the prime power factorization and find the largest exponent of each prime that occurs in both. For these two examples, that would be 2 squared times 3 squared, and that would tell me that the GCD of these two numbers is 2 squared times 3 squared. I don't have an 11 over here, so 11 isn't eligible. Here I have a 2 cubed, but here I don't have 3 powers of 2, I only have 2 powers of 2. For each prime, I go and I take the prime, if it divides both of them, I write the prime down, and then I take the smaller of the two exponents and write that down. And that's another way that I could get this GCD.